Now I'm thinking about a way to remember how to deal with bomb calorimetry problems. So the first thing is that in this case the processes are run at constant volume. Because it's a constant volume, then there is no work associated with the process that I'm looking at. And since there is no work associated with that, then all the heat, in this case QV, is going to be equal to the change in the internal energy of my system. Now, every single time I think about calorimetry, I always have to think about it in terms of the calorimeter being made out of two components. The first component is the reaction chamber, and the other part is water. It's easier to measure a change in the temperature for water. So these two components are gonna be making up what I call a calorimeter. That's always important in every single problem. That's always important to make that to have that in mind. Now, when it really comes to solving the problems, what we want to calculate is an amount of heat that is related to the calorimeter. The whole calorimeter setup, the bomb plus the water, is going to take it's going to take the amount of heat that the reaction is giving up. So I need to calculate the total amount of heat that the calorimeter setup, bomb plus water, is absorbing. Now, there are two different kinds of examples that I'm going to find out when I go into solving problems. The first type of problem is there is no reference whatsoever to anything of those two components. They only refer to, and they only give me information for the calorimeter as a whole. There is no information for individual water or individual bomb calorimeter. They both are embedded just in the information that I have for the calorimeter. When that is when that happens is because it's already assumed that we have a fixed amount of water. The bomb device, it's always fixed, no parts are changed. So now in these kind of problems, we are talking about the whole calorimeter setup. Okay, bomb plus water. All the information is already embedded in the heat capacity for the calorimeter. So if I already have the heat capacity of the calorimeter, then what I need to calculate is the heat of the calorimeter given by by the heat capacity of the calorimeter times the change in the temperature that is recorded for that particular case. Now, the second type of problem that I'm going to find is that I actually have information for each of the two components of the calorimeter. Now I have information for the bomb calorimeter, which, remember, in this case it's always fixed, but I also have information about water. And in this case, the clue is that I'm going to be given a mass of water. Because the water itself can change from experiment to experiment, I can put less or more, and then by controlling the mass, what I need to know is the specific heat capacity of water, so they can scale up or down depending on the amount of mass that I have. The other piece of information is I'm going to be given a single change in the temperature that corresponds to both the bomb and the water that it's contained in the bomb calorimeter. The equation that I'm going to be using is, since I have two components now, then what I need to know to calculate the total amount of energy is whatever energy goes into the bomb and whatever amount of energy goes into the water. Looking at the data that I'm going to be given in the problem, for calculating the heat of the bomb, what I'm going to be needing is the heat capacity of the bomb plus the change in the temperature. Whereas for water, since I already know the mass of water, I also need to now know the specific heat capacity of water times the change in the temperature. In the end, I calculate these two. The sum of these two is going to give me the total amount of heat for the calorimeter. Now, the other relationship that I need to remember is this one, that it doesn't matter what kind of problem you have, problem A, problem B, in the end, this relationship is always true, that the total heat that it's taken in by the calorimeter is equal to the total amount of heat that the reaction is given off. That's why in one case we have a positive sign and in the other case we have a negative sign. All the problems will follow this logic. Either you have one or the other set of information, but at the end, we are able to calculate the heat for the calorimeter from the different contributions and then establish this relationship between the heat of the calorimeter and the heat of the reaction.